covariance is a measure of association, and covariance does not capture causality. That was solved by Pearson when he figured out this measure as an advantage, but nowadays it's regarded as a disadvantage. The fact that you have two variables that covariate together does not imply a causal relationship. The fact that x and y move together does not necessarily imply that x is causing y. It implies only that they move together. And we, in a financial system, in an economic system that we have many variables, we may have these animals moving together because they depend on a third variable that is causing them to. Okay? So the covariance is the expectation. So remember, whenever we see expectation, it means on average, how on average x departures from the center when y moves away from its center. So how they co-move. The idea is taking the variance to the bidimensional contest of x and y. The idea of the variance is the expected value of x minus mu, right? The departure squared. We can think then as the expected value of x minus mu times x minus mu, and we simply express this definition to remission to two variables. Rather than putting here x and the mean of x, I put here y and the mean of y. So I'm stretching the definition of variance to the context of covariance. But because it's founded in the idea of the variance, and we are crossing the units, we have the same problem that with the variance. We mentioned before that variance have a problem with interpretation. What are the variance, the units of the variance are? This is even more clear in this context because we will have a kind of cross product there. What is the units of these two guys? So in order to get rid of the problem of the dimension of the covariance, we standardize the covariance to construct something that depends on the covariance. So the information conveyed by the covariance is impounded here in the correlation, and the advantage is that correlation has a kind of well-defined support. It's a coefficient, so it's free of units. It's something that moves between -1 and 1. So correlation, which is a covariance normalized by standard deviations, has this property and allows us to give an interpretation in the sense of strength. Zero correlation is only possible if we have zero covariance, and zero correlation, zero covariance means that two variables are not linearly dependent. And this is something that I want to remark later. If they are not linearly independent, then covariance is zero. If we move away from that context because the covariance is not zero, then correlation is capturing something. To abound, one means perfect correlation, so they move together. It's a kind of redundancy. One is a linear combination of the other. One increases, so does the other. And negative correlation is exactly the same thing, but in the other way around. When one increases, the other decreases. So one aspect is important to remark in this context is the idea that covariance is capturing a form of dependence, but only a form, linear dependency. So remember, linearship means that one can be written as a function of x in this particular way. That's the linear dependency, but there may be other forms of dependency. Y could be written as a non-linear expression of x. Now, covariance is meant to capture this thing. If y depends on x in a non-linear way, the covariance may fail to capture that thing. So zero covariance does not mean independence. Many people take that wrongly. X and y, if x and y are independent, meaning they are not related whatsoever, then the covariance
between X and Y, and hence the correlation is zero. If they are not related in any way, the covariance, which is capturing a specific form of dependence, will tell you they are not related. But the fact that the covariance is zero does not necessarily imply independence. They are not related in this way, but they may be related in this way, or in other way. Okay? Many people take, and you see it's kind of embarrassing when you see people for you guys it's okay, you are still learning, but when you see people, senior people in the academy saying, okay, the correlation is zero, the beta coefficient is zero, so we don't have dependence between two variables. No. You don't have linear dependency, which is what this measure is meant for, all right? And correlations. Now, for us, covariances and correlations are super important because when there are different ways in that we can characterize risk. Variance is a way to characterize risk, but it's not the most important one. For us, in financial markets, we tend to understand risk as covariation. There is a risk source, there is something that introduces risk, and we call that thing risk factor. And your wealth, your portfolio, is a function of that risk factor. You are exposed to that risk factor. And in the context in that we typically try to characterize, you are linearly related to that risk factor. You believe that your wealth, your return can be written, something like that. And because we believe in random relationships, you may have certain additional sort of noise. But for instance, the return of your portfolio is one is driven by this risk factor, is exposed to that risk factor. So in finance, risk is characterized by exposure, by covariance with the risk factor. And the question is, which are the factor or the factors that matters? And we are going to discuss that in chapter 2. The most important one, the most important risk factor is what we call market. The market. So, think about the market as a whole. And the market goes up, and the market goes up for reasons that we don't understand. For reasons that may be random, that maybe we don't understand that. We know that market goes up, so a good day, and the market goes down. It's like a tide. When the market goes up, everybody's happy. When the market goes down, everybody's depressed. How you move, how your wealth moves with this tide, this exposure, this sensitivity to the market risk is one of the most important considerations in finance. And this is called the beta. And beta is a normalized covariance. It's like that, only that it is not normalized in terms of the correlation. It is normalized as an OLS coefficient coming from a regression. But it's capturing how much your return changes whenever the market as a whole changes. If you have a great exposure, you have a high beta, and when the market goes up 1%, your portfolio will increase more than 1%, because it's a kind of leverage effect, it's a kind of multiplier. When the market goes up, I go up more than the market, and hence I'm super happy. Yeah, but bad news as well. When the market goes down, because I'm super exposed to that movement, and the movement is against me, now it takes me down more than 1%. This is the beta coefficient. So for us, risk is not about volatility, variability. That was like the first generation, the first understanding, the primitive understanding of risk. Right now, we model and characterize risk in these terms. There are certain risk factors, we have identified those risk factors, how my economic position changes whenever that risk factors change. What is the exposure to the risk factor? And there are a number of factors, and there are a number of risk sources that may matter to you depending on your activity. I'm exposed to, trading with a foreign country. Currency is a risk factor to me. I invest in different countries, matter a lot. For instance, policy, the local government policies, etc., stability, those sort of things will matter a lot to me. You have questions? No. All right. So correlations allow us to also to characterize how things can move together. And in terms of in chapter 2, when we talk about the diversification and portfolio benefits, it is important that we ideally should observe low correlations. If the market goes up and my wealth goes up, I'm super happy. When the market goes down, I'm not be so happy. I would like to diversify by investing in different things. So I need small correlations, because if you tell me that at the end of the day, when the market goes up, all my different investments go up, and when the market goes down, all my different investments, all of them go down, it's a kind of redundancy that essentially spoils the benefits of diversification. What's the point of investing in different things when at the end of the day, everything moves together, right? So unfortunately, if we examine correlations between, for instance, sectors, this is correlations between in the US market, when we group all stocks in just 5 sectors: consumer, manufacture, high technology, health, and everything else. So we group all stocks traded in the US market into these 5 categories. And we compute correlations to observe correlations which are not smaller than 70%. So pretty much this tells you that by investing in different stocks in the market, you will learn the diversification benefits. You buy Tesla, you buy IBM, pretty much all those things move together. If you want to get benefits from diversification, you need to consider different classes of assets. You will have to invest in bitcoins, gold.
Spider too, right?
What?
Because Spider, like ETF that goes against.
ETF. Well, ETFs had a bubble. They saw an illusion. At the beginning, it was a very successful thing before the crisis in 2009. They saw the idea that they were able to diversify. They have a very strong diversification benefits because they were able to sort of merge different investments with very little correlation. So they became super popular before the financial crisis. And in the financial crisis occurred something very happy. Sorry, but happy. Not happy for them. For people doing research. So I'm happy. Like a lot of selfies. Something very interesting. Let me put it in this terms. Something very funny. And the thing was that stocks that were not assets, that were not correlated during good times, became super correlated during bad times. So the correlation was kind of state dependent. These guys have been able to find assets that were little correlated during the good time before the crisis. When the financial crisis erupted in 2008, 2009, those investments moved together. The correlation, this is kind of unconditional correlation, overall correlation if you like, is depending, reality is depending on the time, on the state of the economy. And financial assets become more correlated during bad times.
So during COVID, what happened?
It happened during the COVID. You saw that perfectly illustrated in the COVID because everyone was losing. So everything was losing.
Why do we diversify? Why don't we join?
That was kind of good. I mean, it was like some, punch in your face. Then you thought that you had, because of course, diversifying has a kind of downside. If I suspect that this is the best stock possible, I should put 100% of my money in that stock only. So I'm paying, I'm sort of giving up potential returns just because of this safety that when things go wrong, a part of the portfolio may fall, but the other will still be okay. And what we observe during bad times is that, no, that feeling is wrong. When things go bad, then the correlations between the assets of the portfolio will increase. So you are overstating the benefits of diversification. It's what we realized in 2008 by the time.
So,
Sorry, if you can speak another question.
I was asking like for example and an explanation of why it happens.
The same thing, people over there, and the reaction is the same and it's predictable, everyone's certain. It's like a COVID. COVID is a perfect example. All the productive activity was deteriorating and things were more systematic than thought.
But is the industry related or are you focused only on the company? Because maybe
This is industry. So company would be even more inclusion capital. You would say, okay, right, this is in the sector, this is going to the industry, so you are sort of going to a deeper layer. But as I said, if you go to diversify, for instance, between countries, you will not work here. So right now, the problem is that the economy has, the ultimate effect is integration in the economy in all levels. And once again, the guy to put the remote is the financial market. It's a financial economy, and the financial thing is integrating everything, it's connecting everything. Because we all go to the same circuits to get funding. We play by the same rules. That's connecting, that's increasing systematicity. And that is really bad news when it comes to a crisis. The whole system.
So why do wealth managers then waste time on diversifying?
First of all, they need to justify their salary. So they need to say, they tell you there is no point in.
Yeah, because otherwise.
If they, I mean, there's many questions, there's many whys when it comes to what fund managers do. Many people is discussing, as you know, saying like, do they give you any value systematically? And these are all investors saying, no, there is no systematic evidence. Actually, I would say there is systematic evidence that the fund managing industry fails to provide systematic alphas. So the question will be, why do you trust a guy that takes the decisions on your behalf? And they will tell you another story. You cannot tell your clients, look, there is no reason why you should pay.
But you're saying.
There is no reason to diversify.
So you're saying like you can diversify across different
Assets.
So like
If
I
you
buy
have,
bonds,
if you
ETFs,
exactly,
then
if
we're
you
gonna
want
stocks.
any chance to diversify, it needs to be across the class of assets. All. It's not going to be stocks only. You need to go bitcoins, gold, whatever. That is ETFs. Get this kind of feeling of diversified.
Well, my point of the ETF, I know there's ETFs that go against S&P 500, that are negatively correlated to.
Yeah.
So basically.
But because you make derivative positions, or you are so serious something you introduce, and where it goes, it can be for you or against you. And at the end of the day, that's a bit. And that doesn't mean that you're gonna have very short diversification. It's just you are just changing the sign of your head. We said it before, right? You believe that Nvidia is gonna fall down. There's a lot of people now betting against Nvidia. Which is bad because if everyone goes against them, they are going to force the price to go down. Whether they are right or not, it's like at the end of the day, the market is a kind of democracy in which you not necessarily, as what we said, puppets. If everybody believes that this is a good idea and everybody buys just because everybody is buying, that's the definition of a puppet. And worse in both directions. If everybody says that this is a bad thing and they sell, they are going to make the stock fall
It's like
down.
when Elon Musk posts on Twitter or X.
They try to manipulate.
Yeah,
Donald
they
Trump is-
put a fight.
They go with this rumor and they have, and they discover that they have a lot of private interest in certain rumors.
Yeah, really.
The same thing. There were a lot of people saying, wow. This guy is breaking his theory, is super borderline in many sense, right? It's like 20 years ago, I think that if you ask anyone in the US, they will say that's impossible to happen in the US. It may happen, in South America, even in Europe. Right, exactly.
Every day.
This happens to these poor guys, not to us. We are there, we are superior. And this is that, same in Europe. We have this feeling of superiority, the moral superiority, these bad things happen everywhere in the world, not in us. And then you discover corruption, political instability. See France. Yesterday, France, the spread, the risk premium in bonds in the 10 years is almost in the maximum because they are failing to have. You see, for instance, the bond of Greece is now cheaper. Borrowing from lending to the Greek guys is cheaper than lending to the French, and it's because of political instability in the country. It's not nothing to do with the economy, with their fundamentals. It's with political issues. Okay,
So,
Yeah,
and
sorry.
just push it back to this, so these closest to one needs to go in the same direction, right?
what? They move in, because that's the positive correlation. They will meet together. A good day will be a good day for the 5 sectors. A bad day, on average, there will be a bad day for the 5 sectors. So the only chance to get some benefits is across class of assets, no in sectors. Okay, I'm gonna give you the condition expectation here. Let me put it down. I will come back later when talking about condition expectations, but let me sort of skip this part, okay? Let me talk about the financial returns in order to move to the hopefully to get some applied analysis today. So financial returns, like we said, what we observe in the market is prices. But prices are non-stationary. They move. And we recognize pretty much this upward trend. This is US prices. You see, you move the mouse, right? You see that it's changing. Some graphs, I have also made this hyperlink. You click on the graph. This is going to go to the Federal Reserve. This is one of the main data providers. I don't know if you know the Fred, you probably have used before. Super useful. They have thousands of time series variables and for free. So if you look at the US market over the last 10 years, it's an upward trend. The US market is always doing well. On average, it's growing, but this is the behavior that we consider as non-stationary. There's not a well-defined mean here. You will say, what is the mean? 4,000 points. That's an index. It's not dollars, it's points. 4,000 points. Yeah, but this average is representative of what we have it over here? No. The index is going over here. And it will go down or it will go up because it's showing the dynamics that correspond to what we have called the drifted random walk. So forget about working with prices. In these graphs, in the economic graphs, it's very common to see these gray bars. Have you seen them before? What is that? Recession. Recession is an economic term. Recession is a technical definition. 3 quarters, 3 consecutive quarters of negative GDP. This is indicated as real recession, as economic recession. Financial recessions and economic recessions are not necessarily coming together. But this is in 2020, so this huge drop, that's COVID. The financial market sort of was matching what was happening in the economy, which is, as we discussed before, right? The whole thing freezing. So we don't observe prices, we observe prices, but yeah. We observe prices, but we don't like prices. We prefer working with returns.
Antonio, the shock in 2025, that's almost the same proportion as in COVID.
No, but you don't see it there.
When
Excuse me, no. You should not make these interpretations in the graph because the scale of the graph is misleading. The proportion, yeah,
It's much lower, yeah, because
exactly.
coming
It's
from
not the same
6,000.
coming from the 3,000 to be nearly 2,000. It's not the same as coming from 6,000 to 5,000. In absolute terms, the magnitude is the same, but in relative terms, the movement, the intensity of the movement is not the same.
It's like half.
So we need to do this interpretation certainly with returns. So in this graph, if we look to units, we go to percentage change. Right? That's returns. So actually in this 2025, we have a large movement. We have big spikes here. You see, this is changes. We put it in percentage change. And that tells us that, for instance, during the COVID, we had like a 15% drop in the prices. That's from one day to another. And then you see what we said before, the relative magnitude of the change is bigger in the COVID. Here we have something like a 5% daily. This minus 15%, you see this graph? Up. This is pretty much 10 years of daily data. And here I can tell you what we are observing. This is not normal. You see the symmetry? See these big spikes here, those unlikely movements, that's going to trigger kurtosis. But we don't have skewness because you see this big movement there, it's not much above, right? This is minus 10%, it's bigger than minus 10. And you don't have here something in that level. That's negative skewness and kurtosis. If we analyze the series, this is highly non-normal. There's no way we're going to say this is normal because we observe here, even just, simply, it's clearly there, non-Gaussian features like that. So this is what we work with returns, because instead of having this non-stationary behavior, returns are much more steady around the average, right? This is the mean. And then we observe other characteristic pattern of returns and prices, which is time varying volatility. If I want to see the average price, I need to figure out the level around which prices are bouncing. And we see that this is pretty much stable. Looks like 0, but it's not 0. We're going to sort of figure out that numbers later. It's not below 0. Analyzing graphs is very tricky. Trying to make conclusions with graphs, because graphs can be super misleading. The scales can be sort of, the graph can be modified. So I know that because those are the standard features, but it's not 0, it's not impossible. It looks like a close to 0, but we will see that it's a kind of excess return, positive excess return. But we would like to see volatility as the intensity of the changes. So in the graph, we see that's the average, whatever the value is, we will figure out later. We see the propensity to change, but right at a canal in which returns are positive, right? And what we observe is a propensity in which samples occur something like this. You notice that? Periods of low variability, periods of low volatility tend to be followed by periods of low volatility, but periods of high volatility tend to be followed by periods of high volatility. Hence, volatility is predictable. We cannot tell in an accurate way how profitable is going to be the market tomorrow. There is no prudent way to determine if tomorrow is going to be a good day or in a bad day, given the information that we have up to today. There is no econometric model. There is no known technique that allows you to tell that thing, which is of course the most important thing if you are an investor. Tell me if tomorrow is going to be a good day, I buy it. Tell me that tomorrow is going to be a bad day, and I sell it. You can tell me, you cannot give me this hedge, I don't know what you're going to have. But if tomorrow, if today is a volatile day, the most likely scenario is that tomorrow is going to be a volatile day. So we have econometric models and techniques that allow you to predict volatility, to forecast volatility, and to capture risk. It's a second best value something. Cultivated and educated investor will exploit these techniques, and noise trader will simply go blind. I don't know, I buy, and if this person is lucky, this will be okay, but just like a casino, if you play once, you may gain today, but if you play very often, the most likely scenario for you is, at the end of the day, you will materialize overall losses, okay? So that's why we work with returns. Now, the question is, how can we compute returns? The returns are computed in two ways. So we need to make clear in which way this return that we are expressing, this is percentage change. So this is what we call the simple return. So the return that is going to be super important for us. Return can be either simple returns, or another weird thing is called the log return. I'm sorry guys, this is what it is. Two ways. We need to make clear in which way the return that we are expressing, we are computing, is measured. So the simplest one, the most intuitive one, is the simple return, which is the percentage change. This is simply the percentage change. So this is what, for instance, the Federal Reserve has computed here. The idea is very simple. I have an initial investment. So let's say that I buy today the stock and I pay PT. So this is my initial investment. At the end of the day, at the end of the period, so remember we are working with this one period dimension, here that will be daily, those are daily returns. So the horizon will be a day for us. At the end of the day, I get a price. So later I can sell my stock for a different price, maybe bigger, maybe smaller, and hopefully that day I can make a dividend. This is going to be a very extraordinary thing. It happens only once a year, maybe twice a year. Not every stock pays every day. So most of the time, this guy will not appear, but theoretically we can consider as a part of the payoff. My final investment is going to be made when it comes to the stocks. It's going to be made by the price and hopefully perhaps a dividend. I want to relate these two amounts. One is a time T, and is my initial investment, and then at the end I have the payoff, which is made of the final price and perhaps a dividend. Most of the time it will not be there, but it could be there. And I need to go from here to there. So this is a stock. How I relate these two amounts which are in different moments of time. So this is the difference between the simple return and the log return. The ingredients are those things. So what changes is how we relate one measure to one thing to the other. Simple return takes this thing. Current price is equal to the payoff if I take my price and I compound it like that, I will get my final payoff. So price at time t and dividend at time, price at time t plus 1 and dividend at time t plus 1. So I use what we call simple compounding. I multiply 1 by a factor which is 1 plus the return. So if we solve this thing for the return, the ex-post return is the payoff in excess of the price. So this is how much money I make in excess divided by my initial investment. So this guy has two components. I can see that this guy comes from a capital gain, which is called a capital gain component. I bought the stock for this price. Later I got this thing. This is a change. It's meaning something in relation to the previous investment. And I may have, in addition, this extraordinary component, which often is not there, but it may, which is what we call the dividend yield. So this is the capital gain component, and this is the dividend yield. This is what the simple return is made of. This is what the Federal Reserve is showing us in that graph. Returns complete according to this law. So this is the simple return. So when we observe there, the minus 10 is minus 10% simple. Alright? This is the percentage change. This is the most intuitive one. This is the one that we all have in mind. But the problem is that there is another way to compound, to do the compounding. And that takes us to the log return. So remember, we invest at time t, the price pt, and at the end of the day, we get a payoff, which is the new price and the dividend. And we want to move from here to there. So I want to relate this amount with something which is in the future, and I need some form of compound. And now we are changing the way in which we compound. I need to take this amount pt and make it bigger. So one way to do that is to multiply by 1 plus r. Another way to make bigger is pt uses a different compounding method. It's not multiplying by 1 plus r, is multiplying by the exponential of r. So I'm going to introduce then a different notation. This rt here cannot be the same that rt there. If I want to introduce, if I want to have the same investment and the same payoff, because we are using a different operation, a different mathematical operation, that return and this return cannot be the same one. So let me introduce here this notation. In the slides, it's called in a different way. I call it simple, and I call it continuous compound. Here I'm going to start. Okay. Continuous compound. Okay. So this is what allows us to go from one way to the other. And if we solve the return, the continuous compound return, then because that involves exponentials, we do the opposite operation to the exponential, which is the logarithm. So that will be the logarithm of the payoff, which is price tomorrow plus dividend tomorrow over price today. This guy goes down here, we undo the exponential by taking the logarithm, and we end up with this operation. And by the laws of the logarithm, by the mathematical properties of the logarithm of this ratio is the difference of logarithms. So this is the same as this amount minus the natural logarithm of it. So we have two ways to compute returns. Simple return, that comes from simple compounding, and log returns that involve exponential compounding. And then you will have a different way to compute the return, and therefore a different numerical magnitude. This simple return will produce a different number than if we compute the log return. So it's super important to determine which units are we using. At the end of the day, they are measuring the same thing. It's just a matter of units. It's like I can give you the amount in terms of dollars and euros, but 100 euros and $100 are not the same. So this is what we need to make clear. You are free to choose how to express compounding and express returns, but you need to make clear which units are involved. It's not the same with the simple return and the log return. Most of the time, you're going to see simple compounding and simple return. So for instance, remember the pricing equation that we saw yesterday. We say price equals the condition expectation under this neutral measure of the future period, and because this is relating past and future, some form of compounding or discounting needs to be involved, and in the expression that I used yesterday, I used the risk-free rate. Now, this is simple. This is the simple risk-free return, because we are using simple compounding. I multiply to take it to the future, I divide to discount. The same operation could be expressed in terms of log returns. Then you prefer that option, the price would be the expected value under the risk neutral measure, but now multiplied by the exponential of minus a risk-free rate, which cannot be expressed in the same units. Then I'm going to use this star. That would be the log return. The continuous compounded return. It's called continuous compounded return or log return. But because continuous compounded is so long for the Americans, even for us, we call it log return. log return because it's a return that can be computed through the logarithmic transformation. So this takes you to this representation. You are working with simple returns, and you recognize that because we are dividing or multiplying by 1 plus something, or you can express things in log returns, and this, for instance, Sam, the expression that you put me before, you were working in your mind with log returns. So you can work with this expression that involves an exponential, and this is very popular in the world of the derivatives. In derivatives, most often you're going to see exponential things. And they talk about returns. Now, a remark is in order here. When they say returns in this expression, they mean log return. And this amount is not the same as that amount. Both are capturing profitability. Those are just two different ways to express return. So they must be related. And what we have is what we call a financial equivalence. Financial equivalence is I invest certain amount, so PT, and I compound this thing with the simple return, right? And at the end of the day, I get some final payment. So forget for simplicity about the dividend. So let's say just I get this price. Or I can do the same thing, but in terms of compounding, of log compounding. So this is going to be with the exponential of a return, which is not the same, because now it's the continually compounded return. I compound multiplying by 1 plus r, so I capitalize, I compound, or I discount when I divide, the opposite operation. I multiply by the exponential, so this is compounding, or I multiply by the exponential of minus, so this is doing the discounting. So this is going to be equal to the price. So what is the relationship between these two things? Financial equivalence is you invest the same thing in the same risk conditions and you get the same payoff. Then these two operations are equivalent. You give me the same values here and the same values here, and these operations are equivalent. So this guy here needs to be equal to that guy here. 1 plus the simple return needs to equal the exponential of the continually compounded or log return. This is the financial equivalence. If you want to know how simple returns and log returns relate to each other, we do that using this expression. So the simple return is the exponential of the continually compounded return minus 1, or the continually compounded return is the natural logarithm of 1 plus the simple return. So they both are connected. They both convey the same information, only that in different units. So what is important here, which is crucial, is you guys tell me which units are you working. And there we are okay. So simple returns, log returns. In the Black-Scholes models, in the derivative, you're going to see this notation. Always. Then you know that when they say returns, they mean log returns. And the assumption of log returns is that they are normal. So they are working with log normal prices. Alright? So guys, we are good. I think that at this point we can sort of work with data. I have like a 20 minutes. When I get some data and get some things here. Just give me an example of the financial equivalence and why it's important to make clear the units, because it's not the same. Keep in mind that we have a bank deposit that is 12%. Now, 12% what? 12% according to the simple compounding, or 12% according to the exponential or log compounding. I keep telling you, 12% continuously compounding, 12% log return. So the question will be, what is the financial equivalent to a 12% log return, which will be the amount that you will naturally see in the context of the Black-Scholes models and in the derivative context. All right, we use the financial equivalence because we want to move from the continually compounded return to the simple return. This is the expression that we need to compute. So the exponential of that 12% minus 1 gives you 12.74 simple. Compound, that will produce exactly the same values you compound over a 1 period horizon. But notice the difference. 12% log return is equivalent to 12.74%. This relationship is mechanical. I will always observe the log return being smaller than the equivalent simple return. Why? Because they are meant to be plugged in a different mathematical expressions to compound. The exponential is more aggressive. Taking the exponential of something goes up very quickly. So the number that we plug in must be smaller. 12% does the same job that 12.74% in the simple law. Okay? So, like I said, guys, it's up to you, but you need to decide. You need to decide, and you need to make clear the limits. In my lecture notes, we by default work with simple returns. So this is the statement. Whenever you see return, what I have in mind is the simple return. The properties are the same. Do I observe a different degree of kurtosis, a different sort of picture when I plot log returns or simple returns? No, because one is the transformation of the other. So if one is not normal, so will be the other. Now, when is it more convenient to use simple returns and log returns? Simple returns and log returns have different properties when it comes to aggregation. And there are two forms in which we can aggregate returns. So, because they are using different mathematical structures, the properties of the aggregation are different. So sometimes it's more convenient to work with simple returns or to work with log returns depending on your empirical application. So once again, remember what I said yesterday, the first day, people in finance are super pragmatic. Why do you do that? Because it's to my interest. It's better for me to work in this way. So what is the property that we like of simple interest? The simple interest has the property of aggregation under portfolio. It is portfolio aggregation. That means that in mind that I have three assets. Asset A, asset B, stock A, stock B, stock C. Each one produce a simple return. So simple return of stock A, simple return of stock B, simple return of stock C. But because I have the three stocks in my portfolio, it's not so important for me how much they produce individually as how much my portfolio produces. So my portfolio have an allocation in which I have invested, let's say, omega 1 on asset 1, omega A, omega B, and omega C. And of course, the sum of all those omegas adds up to the unit. I have invested 40% in A, 40% in B, 20% in A. So what is the overall return on my portfolio? Now, the simple return has this nice property, which is the simple return of the portfolio as a whole is the weighted average of those simple individual returns. You take the return of A, B, and C, and construct this weighted average, building with the weights that you have allocated in the portfolio, and you get the simple return of the portfolio. So it's super simple, and for that reason, when we work with portfolios, we prefer returns, simple returns, because they have this property. Now, this is not true with the continuous component return. The continuous component return is not the weighted sum of the continuously compounded returns of your individual assets. This property is lost when we did this form of aggregation. So for that reason, we prefer working with simple returns in the portfolio context. Now, when log returns are more advantageous, right? When working with log returns have a difference in terms of some payoff. Well, the answer is they have an advantage when it comes in a different form of aggregation, which is time aggregation. So when we aggregate returns in a scale which is not across stocks, but over time. So let's say that I have a week, 5 days, and I have the return on day 2, 1, return on the day 2, return on the day 3, 4, and 5. And of course, I would like to compute the weekly return. I have made 3% on the first day, 2% on the second day, minus 2% on the third day, 4% in the fourth day, 6% on the 5th day. And my question is, 5 days, 5 periods, but total, how much I have made? What is the return over the weekly horizon? Now, the continuously compounded return over the overall horizon is the sum of the individual continuously compounded returns. So you have 3 days in log returns, and you just need to sum up those 3 returns to make the total return of your investment. And this is super nice, and we like these operations. So if you are thinking of aggregating returns, and in derivatives, where you have investment over multiple horizons, this is kind of more handy. So that's why you will prefer, you will see naturally expressed in the derivative context in which you make an operation which involves a period of time, the log return. This property is lost in the simple dimension. This is not true when you are working with simple returns, because the simple return will involve a compounding. This is the advantage of working with logarithms. The product of logarithms is the sum of logarithms. So it has this mathematical advantage. Okay?
And with bonds, we also work with this type of returns.
With bond, I'm not talking about which kind of asset, I'm talking about returns. Whenever you have return of whatever, constructed in this way, you will have these properties. If you aggregate, so A may be a stock, B may be a bond, C may be cryptocurrency. The simple return of such portfolio will be the weighted sum of the simple returns. And that property will not carry over the conditional component returns.
And in that case, the dividend yield would be, like the dividend paid off would be the coupon.
Yeah, no.
right?
And the dividend will be in the final price that they
But
pay.
in the case of a bond, the extra income between the periods of PT and PT plus 1, in the case of a bond would be the coupon, for example.
The payoff, exactly. So we talk about initial investment, the capital investment, if you like, and then you will have a final capital, which will be the total payoff. The total payoff of a stock is price plus dividend. The payoff could be, for instance, just a coupon, in case of a bond, which is just paying the coupon, but the coupon has not redeemed the nominal, the face value yet. So in a bond is more complicated because you have these 2 scenarios. It will be just coupon or coupon plus
Let's say it's
plus payoff. Is understood, guys? Yep.
On the case of simple return to the time aggregation,
On the, showing the what?
on the time aggregation for the simple return, you said that, I know the law of logarithm doesn't hold different returns, so what will you do there? Just like compound?
The log return is the one that.
No, I'm saying, I know, so if you were to compute time aggregation with simple returns, how will you go?
You need to compound multiple times, and that's going to be painful. So imagine that you have just 3 periods, okay, to make it simple.
Also, a follow-up question from that one. When you ask for a loan, that rate is compounded
What?
for the rate. How do you, when you calculate interest, you have 2 ways of doing
That's
that.
the yield to maturity.
Yeah, right,
You will compound something, you will determine something that is going to be simple, and that's yield to maturity. So in your answering your question, right? Imagine that you have 3 returns, R1, R2, R3, and you want to compute the total return. You will have to do this operation. You need to compound with this return, then you need to compound with the second, and then you need to compound with the third one. And that will give you, that will be equivalent to 1 plus the overall 3 period return that you have iterated. So this is called a geometric average. The simple return, right? If you want to compute the simple return in this 3 horizon period, it would be like that. Minus. So it's more complicated to do this 1 plus, right? Because it involves the compounding factors. The same thing goes with the logarithms. But of course, when you multiply the exponential of the first return, the exponential of the second return, blah, 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 the log return is the sum of the 3 of them, because of exponential. So everything becomes simpler. And as I said, people in finance, we are very pragmatic when it comes to that. Is understood, guys? Sorry, because whenever there are like multiple ways, people get confused, like why should I turn left, should I turn right? It's up to you, but one thing needs to be clear. You need to state the units, and then you're safe. And of course, when it's in the other way, if I using the same writing, say, I ask you to do this in the simple return, you are not free anymore. You need to compute simple returns and to work with simple returns. Well, guys, so pretty much this is it. I have just 5 minutes, so I'm not gonna push too much. We're gonna start this workshop next class. This is what we're gonna do for the next day. We're gonna get those S&P 500 data from the Federal Reserve that we have there, right? We have 10 years data. It tells me 5 years, let me go 10 years. We're gonna get something more. Then we're gonna compute simple and log returns. Because we are learning, we're gonna have, like we do in finance, whenever we have to, we need to satisfy our referees. Referee may ask A or may ask B, most normal time, we do both. You may ask me A or B, take it, and give you both. Then we are gonna compute those moments that characterize the stuff. We're gonna work with the daily mean and the annualized mean return. And we're gonna discuss why we need to do that. Those are important conventions that you guys need to learn. These type of questions are my favorite for the final exam. Get this data because it's really applied and involves this practical knowledge and it's a way of testing. So please guys take note of the things that we are now. Annualized mean, annualized volatility. Those are basic measures of performance. In an investment, how much should I get? And this is risky. All right, you may understand risk in a first, in a naive approach as the variability. How much variability should I expect in the characteristic investment in the market, which is the S&P 500, taking as a representative portfolio. Then we are reporting skewness kurtosis, the same thing. Is this normal or no? We're gonna apply, we can sort of check that question, and we're gonna do that formally. I'm gonna introduce one test, one statistical test. It's a very bad test actually, but it's super well known, the Hartley-Pega test. We're gonna formally test using this test whether those stock returns are normally distributed or not. I may say, you know, they don't look normal for me. That skewness is negative. Yeah, but you know, negative enough. We are tested formally, and you know, no surprises. We should reject normality immediately. Then we're gonna report risk measures. All right, volatility is a way to understand the risk, but it's not a natural way of understanding for many people. Volatility, variability means dispersion. But for many people who invest in the market, risk means chances of losing money. Uncertainty means dispersion, change. But change means chances to get money or lose money. You see what I'm saying? Uncertainty means that I don't know what is going to happen to my money. I may lose or I may win. But for many people in the market, they don't perceive the possibility of gaining money as a risk. Yeah, I don't know if I want to make 5% or 10%. That's not a risk for me. As long as I'm gaining money, I don't care. Many people understand risk as the possibility of losing money. We call that downside risk, to distinguish from this other perspective. People are really, really afraid of losing their money. Downside risk. So we have different measures of value of downside risk. The most well-known one is called value risk. Have you heard of that? Value risk? Value risk is a percentile. Value risk is with a given probability, so typically something like the 1% chance or 5% chance Look at the 1%. With 1%, so think in terms of percentiles, 1% means 1% to the left, 99% to the right. So there is just 1% chance of losing more money than certain amount. Value at risk as a percentile is how much money I can lose with a given probability. So 1% value at risk is that there is just 1% chance of losing more money than this threshold. Okay, what is the threshold if you invest in the stock market, in US market? With a 99% chance, you will be in a region. How much is that? This is a super important metric in the banking industry. So important that to cultivate your sort of knowledge of that, I give you some sort of additional footage, so to speak. You go to the marketing hall. Here is, I'm going to use these movies. I don't know if you've seen them. There are two, the 2008, 2009 guys. Is something that you should be aware of those things because it's fake. The nice thing about economics is that things tend to be repeated. So when you go to your interviews, you're going to go and face questions that probably can be related to this background. So invest time in learning these sort of things. And I'm going to give you two movies. You can go there, you see, right? It's like for instance, Margin Call. You click there, they are in the YouTube, they are in English. This is two of the most well-known and fair movies that they have done. Margin Call, I don't know if you've seen it, guys. It's a movie, but it's super nice. It's full movie. So it's there. I don't know why this is completely violation of legal rights, whatever. I don't know why. But they are. So just if you want to learn something interesting, and I strongly advise you in the position that you are, it's going to be just, instead of, I don't know, watching all the stupid movie, going to, I don't know, dance. Yeah, that's one of those things that watch those. This is Margin Call and Inside Job. Inside Job is a kind of documentary.
Sí, it's a documentary buenísimo.
To me, it's super rigorous. There are a couple of professors. There is a Columbia professor there. There is a Harvard professor. The Harvard professor, part of my notes here I'm taking from him, which is a guy in his framework. And this guy, you see when they ask, the guy is so good, putting it, in the corner, and the guy is like, John Campbell, oh my God, I can see a super brain in my feet. And this guy, you see, he's not swollen, like, oh man, he's scared. You guys have to see, and it's for your sake. So Margin Call is describing, is of course pure fiction, but it's basically what happened to a bank that goes into the bankruptcy in 2008, 2009, and all the process that's involved. For your culture, this is super important. The value at risk concept is explained and plays a crucial role in what happens in this movie. My advice for you guys, watch the movie. Next week we recommend. You can watch the movie Margin Call. You can see this video. This is a video of one random guy, I don't know, but he explains very
The movie doesn't show it exactly, but the
and he explains what value at risk, the quantities of value at risk, and then next Monday, we're going to compute that value at risk and that matrix. All right? Not too much homework, watching movies.
Is good homework.
Para